Hello students, Nuclei set 3. Topics to be covered are nuclear energy, nuclear fission, nuclear reactor, nuclear fusion, energy generation in stars, and controlled thermonuclear fusion. Nuclear energy. The curve of binding energy per nucleon versus mass number tells us that the binding energy per nucleon is nearly a constant, that is 8 mega electron volt for nuclei in the middle mass region between A equal to 30 and A equal to 170. The binding energy per nucleon is less than 8 mega electron volt for lighter nuclei whose mass number is less than 30 and for heavier nuclei with mass number greater than 170. If lighter nuclei or heavier nuclei transform to a mass region of A equal to 30 to 170, there is an increase in total binding energy or decrease in total mass. Such processes are exergic and will liberate energy. Two such processes are nuclear fission and nuclear fusion. Conventional energy sources such as coal, petroleum, or natural gas liberate energy when they are burnt. The energy liberated for per kg of mass used is of the order of 10 power 7 joules. The energy liberated in case of nuclear fission of per kg uranium is 10 to the power 14 joules. Thus, nuclear energy sources produce more energy when compared to a normal chemical source. Nuclear fission. Nuclear fission is a kind of nuclear reaction observed in the isotopes of heaviest elements. Neutron-induced nuclear reaction is also called fission. Nuclear fission is a process in which heavy nucleus splits up into lighter nuclei of comparable masses, releasing 2 to 3 neutrons and large amount of energy. For example, when neutron is bombarded with uranium, it breaks up into two intermediate nuclear fragments called barium and krypton, along with the release of 3 neutrons. When a neutron is bombarded with uranium, it can also produce other pairs of mass fragments such as xenon and strontium with the release of 2 neutrons, antimony and pneumonium with release of 4 neutrons. The fragment products that are released are radioactive, hence they emit beta particle to achieve stable end products. The energy released for per fissioning nucleus is of the order of 200 mega electron volt. The energy released during the fission reaction is called disintegration energy, which will appear as kinetic energy of the fragments and neutrons, but later will be transferred to the surrounding matter as heat. Nuclear reactor. Nuclear reactor works on nuclear fission. During each fission of uranium, a large quantity of energy is released along with 2 to 3 neutrons. The neutrons that are ejected during fission may cause further fission, releasing furthermore neutrons. This process continues and the reaction becomes self-propagating. This is known as chain reaction and was first suggested by Enrico Fermi. Chain reaction can be of two types. One is controlled chain reaction and the other is uncontrolled chain reaction. In one type of chain reaction, the number of fission producing neutrons is kept constant. Such reactions are called controlled chain reaction, and the power or the energy released at a definite rate. This is the principle behind nuclear reactor. In the other type of chain reaction, the number of neutrons is allowed to multiply indefinitely. Hence, the energy is released in a very short interval of time, resulting in a violent explosion. This is an uncontrolled chain reaction. Uncontrolled chain reaction is the principle in atomic or nuclear bomb. The first nuclear reactor was built by Enrico Fermi and his associates in 1942. Nuclear reactor is a device in which controlled fission chain reaction takes place. The components of nuclear reactor are nuclear fuel, moderator, control rods, coolant, reactor shield, and reflector. Components of nuclear reactor. The fissionable material used in the reactor is called the reactor fuel or nuclear fuel. One such material is natural uranium. Natural uranium is filled in long narrow metal aluminum tubes called fuel rods, which are placed some distance apart. Moderator. Moderators are used to slow down the neutrons to thermal energies. The neutrons released in the fission reaction have an energy of 2 mega electron volt. At this energies, the probability of neutrons producing further fission is less. Hence, they are slowed down to thermal energies of the order of 0.05 electron volt. The commonly used moderators are water, heavy water, and graphite. The growth rate of neutrons in the reactor is measured by multiplication factor. Multiplication factor is defined as the ratio of number of neutrons produced in one event to the number of neutrons produced in the preceding event. If K is equal to 1, the fission chain reaction will be critical and nuclear reaction takes place at a steady rate. If K is less than 1, the chain reaction will be subcritical and the rate of reaction decreases until it finally stops. If K is greater than 1, the fission chain reaction will be supercritical and the rate of reaction increases exponentially. Control rods are used to control the rate of reaction by observing the excess of neutrons. The fission rate can be controlled by controlling the length of the rods inserted into the core. Commonly used materials are cadmium and boron. Reflector. The reactor chamber is coated with a material which can reflect back neutrons leaking out of the surface of the core. Graphite is the commonly used neutron reflector. Coolant. It is used to extract heat produced in the core of the reactor. The coolant is circulated through the core with the help of coolant pump. The coolant absorbs the heat from the core and transfers it to the heat exchanger. Then water is pumped into it. As a result, steam is produced, which is used in power reactors to run a turbine and generate electricity. The commonly used coolants are water at high pressure, pressurized carbon dioxide, molten sodium, etc. Protective shield or reactor shield. Protective shield is used to protect the people working near the reactor from harmful radiation. It is usually a concrete wall of thickness 2 meter. Like any other power reactor, nuclear reactor also generates considerable amount of waste products. But nuclear waste need special care for treatment since they are radioactive and hazardous. Safety measures for reactor operation and reprocessing of spent fuel are required. A permanent solution for disposing nuclear waste is not yet found. And these safety measures are a distinguished features of Indian Atomic Energy Program. Nuclear fusion. It is a process in which two or more lighter nuclei combine together to form a heavy nucleus. The mass of the product nucleus is slightly less than the sum of the masses of the two lighter nuclei fusing together. This mass defect results in the release of enormous amount of energy. Some examples of the nuclear fusion reaction are H11 plus H11 will give us deuterium plus positron plus neutrino and the release of 0.42 megaelectron-volt of energy. Similarly, deuterium and deuterium combine to give a light isotope of helium, neutron and 3.27 megaelectron-volt of energy. Deuterium and a deuterium combines to also give us a tritium, a proton and 4.03 megaelectron-volt of energy. Fusion is always achieved by raising the temperature of the system so that they get enough kinetic energy to overcome the repulsive behavior. Hence, it is called as thermonuclear fusion. For fusion to take place, two nuclei must come close enough so that the attractive short-range nuclear force is able to affect them. However, since both are positively charged particles, they experience Coulomb repulsion. Hence, they must have enough energy to overcome the Coulomb barrier. The height of the barrier depends on the charges and the radii of the two interacting nuclei. For example, if the barrier height of two protons is of the order of 400 kilo electron volt, the temperature at which the protons in the proton gas would acquire enough energy to overcome the Coulomb barrier is 3 into 10 power 9 Kelvin. Thermonuclear fusion is the source of energy output in the interior of stars. The interior of the Sun has a temperature of 1.5 into 10 power 7 Kelvin, which is considerably less than the estimated temperature required for fusion of particles of average energy. Clearly, fusion in the Sun involves protons whose energies are much above the average energy. Fusion reaction in the Sun is a multi-step process in which hydrogen is burnt into helium. The proton-proton cycle by which it occurs is represented by the following set of reactions. For the fourth reaction to occur, the first three reactions must occur twice, in which two light helium nuclei unite to form an ordinary helium nucleus. Thus, four hydrogen atoms combine to form a helium atom with a release of 26.7 mega electron volt of energy. Helium is not the only element that can be synthesized in the interior of the star. As the hydrogen in the core gets depleted and becomes helium, the core begins to cool. The star begins to collapse under its own gravity, which in turn increases the temperature of the core. If the temperature increases to about 10 power 8 Kelvin, fusion takes place again. But this time, helium nuclei is converted into carbon. This kind of process can continue generating higher and higher mass number elements. But elements more massive than those near the peak of the binding energy curve cannot be produced. The age of the Sun is about 5 into 10 power 9 years, and it is estimated that there is enough hydrogen in the Sun to keep it going for another 5 billion years. After that, hydrogen burning will stop and the Sun will begin to cool and will start to collapse under gravity, which will raise the core temperature. The outer envelope of the Sun will expand, turning it into so-called red giant. Nuclear fission and nuclear fusion. Nuclear fission is a process in which heavy nucleus splits up into two lighter nuclei of comparable masses, releasing 2 to 3 neutrons and a large amount of energy. Fusion is a process in which lighter nuclei combine to form a heavy nucleus. Fission reactions take place at ordinary temperature, but fusion takes place at very high temperature. Fission reactions can be controlled, but fusion reactions cannot be controlled. Energy released per fission reaction is more and energy released per fusion reaction is less. End products of fission reaction are radioactive. End products of fusion reaction are not radioactive. Controlled thermonuclear fusion. The natural thermonuclear fusion process in a star is replicated in a thermonuclear fusion device. In fusion reactors, the aim is to generate steady power by heating the fuel to a temperature in the range of 10 power 8 Kelvin. At these temperatures, the fuel is a mixture of positive ions and electrons, which is the plasma state. The challenge here is to confine this plasma, since no container can withstand such a high temperature. Several countries around the world, including India, are developing techniques in this connection. If it is successful, fusion reactor will supply unlimited power to humanity.